controller as a cyber physical system, right? An intelligent model-based system. We could actually use the controller to push the redesign of the components in the actual aircraft itself. And so normally what happens with, especially with like turbojets and aircraft, after the aeroplane has been built, they design a controller. And then they kind of optimize the controller, and then they realize, oh, we could have designed these components a completely different way, but it's too late because we're already in the airplane and we've already got an engine, so nobody's going back to do that again. So we decided that what we do is we design this model-based controller, and the actual controller optimizes the model, and then it produces a heat map or a component map, which I then give back to the designers, and they use it to redesign the components, which gives us a much better response time, and now I can cut down on the stall margins, and so they give me back the components, I tweak the controller, and we go around in this iterative cycle until we've got like a really optimal design. So it turned out to be pretty cool for everybody. So here's how it works. So down at the bottom, you'll see that we've got a fuzzy neural controller. We've got our hybrid electric turbofan planned. And then what happens is I send them some new stall margin constraints. So basically, I have to run the full physics envelope of the model of the airplane about 5,000 times, and then look at it over the full flight envelope. And then I can actually send them new stall margin constraints. And from the stall margin constraints, we can actually get new component maps. We'll go through the different components. And from the component maps, we can then go ahead and take a look at the stall margins. And the stall margins are the places where the engine is going to stall out. So what you really want to do is you want to keep the operating line way away. So if you look at the top right, you'll see the stall line is at the top. That's really bad. Don't be on a plane where the operating close to that red line. You're going to fall out to the sky. And the operating line is at the bottom. And then there's two components. There's uncertainty, and the uncertainty actually contributes to the steady state components. And then there's the transient. And the transient is when the aeroplane comes out to steady state. So for instance, if a pilot experiences turbulence or has to accelerate really quickly. And what we can do, once we've got a new component model, we can redesign and then look at the new stall margins, and from that we can get a much better stall margin stack up, and so we can push the operating line a lot closer to the stall line, and so we can plug those parameters back into the intelligent model-based system, and then we go in this iterative loop until everybody's happy, and we have a controller and they have a hybrid electric propulsion aircraft. This is what we do. So, it's a big team. One of the things that we've done in most traditional engines or turbofans or turbojets, there's actually no way to really measure like the inlet temperatures or the outlet temperatures at various stages to the cycle. And so Mesoscribe is a industry that, a business that is designing these fast response sensors, and these fast response sensors are embedded using 3D printed into the new components. And that gives us a lot more information for the controller, and because we've got a lot more information for the controller, we can look at the health parameters of like the combustor and the turbine, the high pressure shaft and the low pressure shaft. Penn State, on the other hand, actually looking at redesigning the high pressure turbines, which are the big fans that keep you in the air. And because they can now embed sensors, they can actually get a reduced tip clearance. And by getting a reduced tip clearance, it means that you get less drag, you increase the turbine efficiency, and we can reduce the inlet temperatures, which we can now measure. Georgia Tech is designing a clean sheet combustor for high combustion efficiency and low NOx. And basically, we spin these components around the system, and every time they redesign them, I put them into my model-based system, spit them out a new component map, and they go ahead and tweak the design. And so, if you take a look now, our baseline engine is a Pratt & Whitney 11,000G. This is actually a geared turbofan, and what that basically means is that the fan can operate at a slower speed than the first stage of the compressor. So if you look on the architecture, it says 1G3823. That means there's one fan, variable here, 3 low pressure compressors, 8 high pressure compressors, 2 high pressure turbines, and 3 low pressure turbines. That's the architecture of the motor that you see the cross section of. And then if you look at the bottom, this is like the basic schematic. And this will show you like the low pressure combustor, the high pressure combustor, N1 and NF. So normally on a normal turbo fan, it's not geared, and so what happens is the fan has to operate at the same speed as the low pressure combustors, which is kind of inefficient. So now we can use that low pressure shaft N1 because it's on a variable gear, and we can use that in our control system to basically get a much more efficient low pressure compressor. And the same thing with the HPC, we can use NT, which is the high pressure shaft, to get a much better performance out of our high pressure compressors, so we can use less stages. So the less stages that you use in your compressor, the more efficient it is. Compresses the air, spits it into that little red blob there. That would be the combustor, so it spits highly compressed air into the combustor, it mixes it with fuel, it spits it out to the high pressure turbine at the back of the low pressure turbine at a really fast rate, and the airplane goes wee and flies. That's basically how that works. So we had to design a steady state controller, and it's based basically on the fuel flow rate. It would scare you to know what you can't control in an aircraft, and one of them is thrust. You cannot control the thrust in the aircraft because you cannot directly measure it. And so what we actually use is a combination of the variables that kind of approximate thrust. We'll go through that later. So the first thing that we do is we do some steady state analysis so that we get the full physics envelope of the plane. Georgia Tech and Collins Aerospace provide that information to me. Then I can go ahead and do a first cut controller based on a max-min system, which is the general system for this sort of controller. And then we use systems design analysis to take a look at the transients and the constraints. This is just a first cut. This just tells us whether the plane will fly, whether it will meet FAA regulations. FAA says you have to get 95% of the power to the plane within 5 seconds. So that's just the first cut. Once we've done that, we can go ahead and do some more DSA. So now we have to look at transient analysis. We want to get rid of the maximum limiters because they basically are way too conservative. And so we have to redesign this control system. But before we do that, we need to add our motor. So now we have a whole different control system for the motor to avoid saturation and rate limiting. We add the motor to the plan, so now we've got a motor and a turbofan. And now we're still just operating in our first cut baseline. And we use this as the baseline for the rest of the designs. And then after that, we start to redesign the components one by one. And we have this operating on a really fast Kintex, 28 nanometer Kintex. In the lab, it's changed to MATLAB and Simulink, and so we basically run that model about 5,000 times. And once we've run it, we can take a look at all of the averages of the flight envelope, and then we can get ourselves some new component maps. And because we've got new sensors in the components, we can design a much tighter control. We can also look at the long-term health of the components, so we can predict when something's going to fail in an engine. And so we've done our first cuts. These are highly computationally intense. You do not want this thing in an aeroplane. You just don't want it. What we really want is something that can basically converge really quickly and control the engine really quickly. And so we went ahead and we're in the middle of designing our fuzzy neural controller. So we have to embed expert knowledge. And so we use a fuzzy controller because we can embed the knowledge into the membership sets. And then once we've trained that, we can go ahead and replace the fuzzy logic with the artificial neural network. And that way we can teach it to self-tune itself. So this is our ultimate goal. Some of the learning algorithms that we use for the nonlinear estimation, because quite frankly, PID control is fine as long as you're in a steady state. It's when the aeroplane goes into the transient state that you really need to have a very robust control. So we're looking at backpropagation, extended Kalman filters, genetic algorithms, and particle swarm optimization. And so, my second wheelhouse is quantum controls. So, how did I get involved in quantum controls? Well, somebody asked me to join a quantum team, and they said to me, if you come look at my lab, you'll find that I have a warehouse full of wires and equipment and stuff, but my experiment is like this big. And I was like, oh. So we went and we talked, and basically we compared it to the Tyrrhenian numbers back when, if you remember, well, I'm sure nobody remembers the ENIAC, but if you've ever visited it in a museum, you'll know it's really big and it's full of vacuum tubes. And so we went from, these vacuum tubes and these huge rooms of analog equipment to a chip in 1980. And we want to do the same thing. This mess that you see at the bottom, which is a University of California Santa Barbara quantum gas experiment. And we want to start doing this stuff completely on chip. And so this is what your average quantum experiment looks like. And I know this is true because I've been in Gabriella's